Hello and welcome to our video on implicit differentiation. Implicit differentiation is a technique we have for finding the derivative of functions that are not written in explicit form. And we're going to talk about the difference we have there between explicit form and implicit form. In fact, that's one of our objectives, along with using implicit differentiation to find the derivative of a function. But what we're going to be looking at with this, and what you have to realize right now, we've been spending a lot of time developing some rules. We have the power rule. We know the derivatives of all 6 of the trig functions. You know how to go and take the derivative of the product of 2 functions, even though sometimes that does get forgotten. You got to remember, if you see 2 functions being multiplied together, how to take that derivative. You also know how to take you have the quotient rule, and we also have the chain rule, and these are all different rules that we have that help us differentiate a lot of the functions that we've been dealing with. Now we're starting to look at what's called implicit differentiation. And implicit differentiation is going to be key for not only section 2.5, which is what we're working on today in the book, but the final section, chapter 6, which is section 2.6, which is really getting into some story problems. It's called related rates, and we use implicit differentiation there as well. So now let's get started, and we'll kind of again review these objectives for today. Again, the first one that we have today is to distinguish between functions written in implicit form and explicit form. You actually have most functions that you've dealt with have always been in an explicit form, and you'll see that in a second. The other one we're going to use implicit differentiation to find the derivative of a function. Now we'll also spend some time talking about why it is we have this thing called implicit differentiation and what it does allow us to do. Let's start out by at least defining what explicit form is, and then we'll see some examples of it. Explicit form means that the variable y is explicitly written as a function of x. In other words, what that means is that the equation is written as y equals. So if I have something like y equals x squared minus 3x, that's an explicit form. Or y equals 1 over x. That is also an explicit form. And when we work with these things, we have a technique for finding the derivative. If I want to find the derivative of y with respect to x on this first one, I would say that the derivative of y with respect to x, and I can just use our power rule that we have. So the derivative of x squared is 2x minus 3. In the second example of an explicit function, we could just say, oh, y equals 1 over x, or I could think of that as x to the negative 1 power. And so I can now say that the derivative of y with respect to x is equal to negative 1 x to the negative 2 power, or just negative 1 over x squared. Now, what does it mean to be an implicit form? What it means to be an implicit form is it's not expressly written as a y equals. Doesn't mean it can't be modified so that it is a y equals, but it won't be written in that form. For example, our second example, y equals 1 over x, that can be also written as x times y equals 1. That's an implicit function. It's not explicitly saying y is some function of x, but we have this relationship. The other thing that you have to remember, though, is that sometimes, like that one, you can easily solve that one for y. You get y equals 1 over x, and you can take the derivative. So really, we don't have really the need for the technique there. But if I had something like 2x plus y cubed minus y equals 4, now that one right there is not written as a y equals, and we would not be able to go and modify that so that it is written as y equals. So in this case, for this second example here, we would need this thing called implicit differentiation in order to find that derivative. Now let's kind of see how this whole implicit differentiation thing works. What we have in this case, I have 2 problems up here. Let me kind of draw a line to separate them here. In the first one, we have that we want to take the derivative with respect to x of x cubed. Please notice how the variables in here, the dx down in the denominator there, and the x, those match. And when that matches, we're just taking the derivative as we normally do. So in this case, I would say that the derivative of x cubed, we know, is just going to be 3x squared. It's just our normal power rule, and we just take the derivative of that problem as we normally would. The whole idea behind implicit differentiation, though, comes into play with this second example. And the issue we have here is that we have the x here and a y here. Those variables don't match. And when that doesn't match, we have an issue in terms of taking the derivative. We can't just use our basic rules that we're so familiar with. We actually have to use, in essence, the chain rule. We have to realize that y is going to be some function of x, and therefore it does have a derivative that we must take into account when taking the derivative with respect to x of y cubed. And so what I would do on that, using the chain rule, I would treat this, the y, as my inside function, and the cube as my outside function. So what I'm looking at in this problem is, I would say, by the chain rule, first thing I would say is my outside function is to the third power, and I know the derivative of something to the third power is just going to be 3 times that something, that inside function, to the second power. And then by the chain rule, I would have to multiply that times the derivative with respect to x of my inside function, which is y. And so what I would get on this problem is that the derivative with respect to x of y cubed comes out to be 3y squared times dy dx. Whenever you're taking the derivative of a problem where the variables here and here, where they don't match, you must remember to go and multiply by, treat it like the chain rule, and multiply by dy dx. Let's look at some guidelines for implicit differentiation. The very first thing you're going to have to do is you need to differentiate both sides with respect to x. You got to remember that it is with respect to x. That way, if you're taking the derivative of something that isn't x, you remember that you multiply that by the derivative of that letter, whatever it happens to be, with respect to x. What you're then going to do, once you've taken the derivative of both sides, you're going to see that some of the pieces on each side might involve a dy dx, and other pieces might not. And so what you want to do is go through and collect all the terms involving dy dx on the left side of the equation, and then move all other terms on the right side. So if you basically, anything that has a dy dx, or again, if you prefer, you can use the alternate notation for derivative of y prime, if that works better for you, if you're more comfortable with that. Anything with the dy dx, you're going to get onto one side of the equation. Anything without the dy dx is going to the other side. Okay? The dy dx, just generally we try to put them over on the left because we're going to end up solving. We want to solve for dy dx. We want to find what that derivative is equal to. So we'll get it over to the left and everything else to the right. Once we have everything with dy dx on the left, what we're going to do is pull out that common factor. So there will be a common factor of dy dx. So I'm going to pull that out from the stuff on the left-hand side, and then I can go and solve for dy dx by just dividing by the quantity. So you'll have a dy dx times some quantity. You divide both sides by that quantity, and you will have dy dx. Now, the other thing you have to keep in mind here is that while this is going to be a derivative of y with respect to x, that doesn't mean that you're only going to see x's on the other side. You will see x's and y's over there. That will still come into play. So don't get worked up if you see multiple variables on the other side. It will still happen that way. Let's take a look at an example of kind of a simple example on this one. We want to go and find the derivative of 2x cubed plus 3y cubed equals 64 with respect to x. So we're going to take the derivative. We want to find dy dx. Okay. So what I'm going to do, as we talked about in that first in terms of the procedure, the first thing I'm going to do is I'm going to take the derivative of both sides with respect to x. So I'm going to go through and take the derivative with respect to x of 2x cubed plus 3y cubed equals the derivative with respect to x of 64. Now, let's start out with the left-hand side, okay? When I take, this is a sum, so I just have to take the derivative now of each piece, since I'm doing the addition there. So I'll first take the derivative of 2x cubed with respect to x. Well, in that case, because the variables match, it's just going to be my standard derivative rule, so you just use the power rule. And I know that that derivative is going to be 6x squared plus. Now we have the derivative of the 3y cubed. But again, now we're taking this with respect to x. So because the variables don't match, I now have to use the chain rule. So again, I'm going to start out by thinking of this as being in parentheses, that y is my inside function, the cube is the outside. And so when I take the derivative of that, I start out, I take the derivative, when I take the derivative of this thing cubed, it's going to be, I'll take the 3 times that 3, so I'll get 9y squared times the derivative of the inside function, which is y, with respect to x. So I'll get times dy dx. Again, if you prefer, instead of saying dy dx, if you prefer to put y prime, that's fine. That's not a problem. Now we just finish it up, take the derivative of the other side. Well, that's a constant, so I know that derivative is going to be 0. At this point, we now need to solve for dy dx. So the first thing I'm going to do is I will subtract the 6x squared from both sides. And so when I do that, I will now have 9y squared dy dx. Remember, I wanted the dy dx is on the left-hand side, everything else on the other. That's why I subtracted the 6x squared. Equals negative 6x squared. And now to solve for dy dx, I'm just going to divide everything by 9y squared. And I get that dy dx is equal to, in this case, I can reduce if I want. In this case, it comes out to be negative 2x squared over 3y squared. And that would be my derivative. That's dy dx. There's nothing else I really would need to do at this point. Let's take a look at another example, and this one's going to be a little bit more complicated, but not too much. In this case, what we're looking at is x squared plus xy minus y squared, and that is equal to 2. So we're going to go through and we want to find dy dx for this particular problem. Now, what you need to notice right away on this, you need to notice that right here, I do have a product of x and y. And because of that, I will need to use the product rule to when I take the derivative of this particular piece. Anytime you see two variables being multiplied together, you will want to use the product rule. So now, for this particular problem, if I want to find dy dx, I'm going to need to go and take the derivative of everything here with respect to x. So I'm going to start out, just take the derivative here, d dx, and I'll take the derivative with respect to x on that too as well. Well, when I take the derivative with respect to x of this whole part right here, I do have to take the derivative of each individual piece, and I do have a product rule here, and that product rule is also going to involve a chain rule because I'm going to take the derivative of y. And right here, I will have the chain rule. So when I take that derivative, in this case, I'm going to go through the derivative with respect to x of x squared. Well, that's one we're familiar with. That's just going to be 2x. Plus, now let's take a look at that next part. When I take the derivative of x times y, I do need to use the product rule. So it's going to be the derivative of the first, which is just, the first is x, so the derivative of the first is just going to be 1 times the second, which is y, plus the first, x, times the derivative of the second with respect to x. So that is just going to be, because I'm taking the derivative of y, it's just going to be dy dx. Or if I want, I can use y prime. Now I get to this third piece right there. And when I take the derivative of that, I do have to use the chain rule. So in that case, I start out with this piece. I got to think of that as being y squared, so it's in the parentheses. So it'll be minus 2 times the inside function. The derivative of something squared is 2 times that something, and that would be, if you want, you can write it to the first power, times the derivative of the inside function with respect to x, which again is just going to be dy dx. And in this case, that is going to be, and then it's equal to the derivative of 2, which again, that's a constant. So for this problem, again, like the last, that is going to be 0. You can have other things over there. It could involve x's over there. It could involve y's over there. But right now, what we've had involves x. At this point now, I want to solve for dy dx. So if you remember, our job at this point is to get everything that has a dy dx on the left-hand side, everything without a dy dx on the other. So at this point right here, I see just a couple of things right here that do not have a dy dx, the 2x and the 1y, or just y if you want. So this piece over here, I'll just kind of rewrite it all in, so it's simplified a little bit. I'll have 2x plus y plus x times dy dx minus 2y times dy dx. Remember, that is to the first power, okay, equals 0. So now I want to go and get everything that doesn't have a dy dx, move that over to the right-hand side. So I'm going to need to subtract 2x, and I'm going to need to subtract y. And so when I do that, when I subtract the 2x and subtract the y, what I'm going to end up with then is x times dy dx minus 2y dy dx equals negative 2x minus y. So now what I want to do, remember we're supposed to solve for dy dx, I need to go and factor out, pull out the factor of dy dx. So I'm going to think of that as in terms of a factoring, greatest common factor. I pull the dy dx out, and I'll be left with x minus 2y, and that equals negative 2x minus y. And the last thing that I need to do is I need to solve for dy dx, so I'm going to divide by, just go and divide everything by the x minus 2y. And so my final answer is going to be that dy dx is equal to negative 2x minus y over x minus 2y. That would be the derivative of that implicit function, implicit relationship. What I'd like you to do now is to use implicit differentiation. We have a relation here, sine of y equals x minus y squared. And I would like you to use implicit differentiation to find the derivative, find dy dx, or solve it for y prime. Okay, so pause the video, do your calculations, and once you're ready, come back and we'll go through what the answer should be on that problem. Okay, welcome back. What you see now, I have the work all down. The first thing I did on this one is, again, to remind myself that I'm working with the chain rule, I put the parentheses around the y's. So I kind of got that in there. I remind myself I have to use the chain rule. So to start out with, then I have to take the derivative of both sides. I have to take the derivative with respect to x of sine of y, and then I also have to take the derivative with respect of x minus the composite function y squared. So when I take that derivative of sine of something is cosine of that something, cosine of y, times the derivative by the chain rule. The derivative of the inside function is just going to be dy dx. And that equals the derivative of x is 1. When I take with respect to x, I don't have to worry about anything because the variables there and there match, minus the derivative of the y squared is going to be 2y. And again, by the chain rule, the derivative of that inside function is dy dx. So right now, after I take the derivative of both sides, you should have had cosine of y times dy dx equals 1 minus 2y times dy dx. Our next task is to go and move everything with a dy dx onto one side, everything without a dy dx onto the other, and we want the dy dx on the left. So right now, the first thing I'm going to do is I'm just going to add a 2y dy dx to both sides. So that gets me to this point right here. I pull out the factor of dy dx, and I have times cosine y plus 2y, and that equals 1. And so I get to my final answer, that dy dx is equal to 1 over the cosine of y plus 2y, and that's all in the denominator of that fraction. Hopefully you got that answer. If not, take a look back at what I did, see if you can identify what mistake you may have made, or if you have any, if you're not sure, or if you have some questions, make sure to write those down in your notes and bring those to class bring those to the next class, and we'll go over those questions with you. Here are 2 additional problems I would like you to try and include these on your whisk, at the back of your whisk, in terms of what you did on these problems. The first one I would like you to do, and again I want you just to find dy dx on this, is I want you to find dy dx when you have x squared minus y squared equals 25. This will be very similar to the first problem we did, the first example, so if it helps, take a look back at that one. In this second one, it's going to be a little bit more complicated because what you have here is the quantity xy to the 1/2. That is actually, you have a product x times y, so you have to use the product rule there, but you also have a composite because of the fact that this is x times y being raised to the 1/2 power. So your outside function is to the 1/2 power, and then you have to take the derivative of what's inside, which is a product. So remember to use the product rule on that when you're taking the derivative of the inside function, and simplify it as far as you can. You don't, if all you do is go through and take the derivative and get everything, get it as dy dx, and without doing any simplification, that's going to be fine. I think that's probably all you're really going to want to do. And I would not go any further than that in both cases. Just get it as dy dx equals and just leave it. So do those problems, include those on the whisk, and we will see you next class, and we'll spend some time looking at implicit differentiation. What happens next is going to be story problems, so be prepared. We're going to be working with what are called related rate problems. So we're going to be talking about things like if water is being added to a tank in by this amount, discussing in terms of how is the height of the water, how's the depth of that water changing, those types of things. So that's what's coming up, and implicit differentiation will be very key with that. So with that, I will say good evening, and we will see you next class.